Hi there, this is a geometry video. It is chapter 6, section 6, and today we will be talking about trapezoids and kites. We have mentioned previously when we talked about quadrilaterals a few sections ago that in the case of trapezoids you have only one pair of parallel sides. In the case of kites, you have no pairs of parallel sides, and we'll get to that in later on in the lesson. So first and foremost, I kind of wanted to give you some anatomy of trapezoids, because oftentimes when you hear the word base, you think bottom, the bottom is the base. And so when you see a trapezoid that looks like the first diagram here on the left, then it's not very complicated to see where the bases are, because they're like where you think they would be. They're going horizontally. And they're, one's on the bottom. So, but we want to be more specific about our bases. The bases for a trapezoid are always going to be the sides of the trapezoid that are parallel. Like we just said earlier, a trapezoid has only one pair of parallel sides. So you can see that the legs are the sides that are not parallel. So here we've written that down. Legs are non-parallel sides. Bases are the parallel sides. And the base angles are formed by because of course angles are formed by two sides. So one of the sides is a base and one of the sides is one of the legs. So here you have a base and a leg, and so angle D is a base angle. And then you have base and a leg, so angle C is a base angle. So we have C and D. And of course this is a base and this is a leg, so this angle is a base angle. So that's angle A, and base, leg, angle B is also a base angle. Alright, so I just wanted to show you that sometimes the trapezoid can be kind of like looking vertically, if you will. But again, the bases are not always going to be top and bottom like they are in the first diagram. But they're always going to be the parallel sides. So here you see the markings for parallel. So you got your parallel sides, and these are your bases and your legs. And of course, a base and a leg makes a base angle. So angle C again is a base angle with B, and A and B are base angles as well. So just some anatomy there for you for a trapezoid. All right, so we want to get to some of the theorems that we have for trapezoids. Thank you. So, and more specifically for isosceles trapezoids. An isosceles trapezoid is a trapezoid in which the legs, which are the non-parallel sides, where the legs are congruent. So you can see here that I've got the non-parallel sides. These sides are marked parallel, and these sides are marked congruent. So when the legs are congruent, you have what we call an isosceles trapezoid. And we have three theorems today for our isosceles trapezoids. The first two are converses of each other. So it says if a trapezoid is isosceles, then each pair of base angles is congruent. So each pair, so we can see from the diagram that would be angle G and angle H would be congruent because they're base angles. And angle F and angle J would be congruent. That's the first theorem. And the second one is basically kind of the converse of it. It says if a trapezoid has one pair of base angles that are congruent, then we know that it's an isosceles trapezoid. It kind of just goes in the direction. And then, of course, we have our last theorem, which is a biconditional statement that says a trapezoid is isosceles if and only if, remember the little notation for IFF, it's not if, okay? Don't say if. Okay, it's going to be if and only if, which means it goes both directions. So a trapezoid is isosceles if its diagonals are congruent, and if its diagonals are congruent, then it's isosceles. It goes both directions. All right, so that's what the if and only if is all about there. So basically what this is saying is that the diagonal FH, which would be this diagonal here, is congruent to GJ. Okay, so in an isosceles trapezoid, the diagonals will always be congruent. So in example 1, it says, if the measurement of angle FJH equals 85, so I kind of want to mark my diagram here, FJH, so here's F to J to H, so this angle here is 85, and then it says FK is 8, and JG is 19, so the entire distance all the way over here is 19. Find each measure. So in part A, it wants angle FGH. So FGH. They want this angle over here. Question mark, okay? So what we know is that let's see here. Okay, so I didn't mention that in the example, but it's actually in the problem in the book. This is an isosceles trapezoid, so I probably should have mentioned that. So let's add that to our directions. We want to put something like F, G, H, J is isosceles. That makes a big difference. Okay? So, because it's isosceles, then we know that the diagonals should be congruent, and we know that the base angles should be congruent. So, if this angle is 85, then this angle over here is also 85. Now, the reason why I'm showing you that is because I already know from before that for any trapezoid, we know that because they're parallel, these two angles are consecutive interior angles, and so they're supposed to add up to 180. So we're going to use that over here to say that the measurement of angle FGH plus 85, which is the measurement of JHG, should equal 180 because the two angles are consecutive interior angles. So then to find FGH, I just subtract 85 from both sides. And then the measurement of angle FGH is going to equal 95. And there you go. And then for KH, we know that the diagonal should be congruent. So we know that FK, which is 8, plus KH should equal 19. Because the segment addition postulate tells us that I can add FK with KH to get the entire diagonal. And then this entire diagonal is JG is 19. And they're supposed to be equal to each other. So that's kind of where I'm getting this equation from. So I'm going to subtract 8 from both sides. So that means that KH equals 11. So not really complicated, but that is how you can apply some of these theorems to find these measure. So now we want you to try this little guy. And I did tell you that it's isosceles, so that's good. And then we will go on to coordinate geometry, where I have already begun the process for you. So it says quadrilateral ABCD has vertices A, -3, 4, so there we got that guy. B is 2, 5, there you go. C is 3, 3, and D is -1, 0. Show that ABCD is a trapezoid and determine whether it is an isosceles trapezoid. So in order for us to determine, or to show, to prove basically, that it's a trapezoid, we have to show that it only has one pair of parallel sides, because a trapezoid, that's what by definition only has one pair of parallel sides. If it has two pairs of parallel sides, then it would be a parallelogram. So we want to make sure that it only has one pair of parallel sides, and for parallel, that means that we're going to want to use the slope formula. So I'm going to go ahead and put the slope formula up here. I'm going to put it down here. Remember that it's y2 minus y1 over x2 minus x1. That'll give us the slope between two pairs of points. And then also we're going to be using the distance formula because they want us to see if it's an isosceles trapezoid. It's an isosceles trapezoid as long as the legs of the triangle, of the trapezoid are congruent, okay? So for the distance formula, if you've forgotten what that little guy looks like, it's the change in x's squared plus the change in y's squared, and the square root of that. So we're using those formulas to help us over here with our... So the first thing I want to do is do opposite sides, so I can see from the diagram that that's going to be A and B. I need the slope of AB. So the slope of AB is going to be, again, y2, so I'm going to say 5 minus y1, which is 4, over x2, which is 2, minus x1, which is -3. And 5 minus 4 is 1. And 2 minus -3 is 2 plus 3, so that's going to be 5. And I get 1/5 for the slope of AB. Then the opposite side is going to be CD. So I want to now find the slope of DC. So again, we're going to go y2 3 minus y1, which is 0, over x2, which is 3, minus x1, which is negative 1. 3 minus 0 is 3, and 3 minus a negative is 3 plus 1, which is 4. So I get 1/5 and 3/4. Because those slopes are not the same, then it means that those sides are not parallel. So AB is not parallel to DC, so that's good. And now I want to check the same for the other pair of sides. So now I'm going to check BC. So we want the slope of BC. So using these 2 points, we're going to take y2, which is 3, minus y1, which is 5, over x2, which is 3, minus x1, which is 2. 3 minus 5 is negative 2, and 3 minus 2 is 1. So we get a slope of negative 2 for BC. And now we're going to try the slope of AD, the opposite side. So we're going to use these 2 points, and we're going to go 0 minus 4. So for my y2, I get 0 minus y1 is 4. x2 is negative 1, minus x1, which is negative 3. 0 minus 4 is negative 4. And negative 1 minus negative 3 is negative 1 plus 3. And negative 1 plus 3 is 2. So negative 4 divided by positive 2 is negative 2. So this time we get the same slope of negative 2. So we know that BC is parallel to AB. And you've confirmed that there's only one pair of parallel sides. Therefore, this is in fact a trapezoid. So we've proven the first part of it. And now we want to know if it's an isosceles trapezoid. For it to be isosceles, then you have to have the legs be congruent. Remember, the legs are the non-parallel sides. So we don't want to use BC and AD because we've already determined that those are parallel. We want to go back to AB and DC and see if they're in fact congruent. So now we're going to use the distance formula. And the distance formula for AB is going to be negative 3 minus 2 quantity squared, and then 4 minus 5 quantity squared. Okay, so negative 3 minus 2 is going to give you negative 5, and negative 5 squared is going to give you positive 25, and 4 minus 5 is going to be negative 1, but negative 1 squared is going to be positive 1. So basically we get the square root of 26. Then we're going to try the distance, that was the distance between A and D. So now we want to try, that was the distance between A and B, these two. Now we're going to do the distance between D and C. So we're going to go negative 1. Okay, negative 1 minus 3 are the x coordinates squared. And then we're going to go 0 minus 3 squared. All right. So negative 1 minus 3 is negative 4, and negative 4 squared is positive 16. And 0 minus 3 is negative 3, and negative 3 squared is positive 9. And then 16 plus 9 is 26. All right? You like my little Spanglish there? All right. Actually, that's supposed to be 25, which is 5, so they're not congruent. Well, look at that. Don't get too excited. Sometimes you want things to happen, and so you just kind of will them to happen. All right, so we actually get 16 plus 9 is 25. So it's not isosceles. So it's said to determine whether it was isosceles or not. So in this case, because we didn't get the same, we got close. I mean, they're pretty close there. And it looks like it's an isosceles trapezoid, but it's actually not. Square root of 26 and the square root of 25, not the same. So not isosceles. Awesome. So now you're going to have a chance to do the same thing with this little guy. Remember to first plot the trapezoid and then show that it's a trapezoid by doing what we did earlier, and then determine whether it's a isosceles trapezoid or not. Okay? So Then we have our theorem here, trapezoid mid-segment theorem. Now we've talked about mid-segments of triangles before, and basically the mid-segment is the segment that joins two sides of a triangle to the endpoints, the midpoint, sorry, the endpoints of, I can't even say this right, the endpoints of a mid-segment are the midpoints of the opposite sides. And so we've had mid-segments before, and so this time we're just applying it to a trapezoid and then have a couple of properties that apply to the mid-segment once a trapezoid. So the first thing we want to be aware of is where the midpoint is. So you can see here that you've got your two sides, and I'm not saying that FD is congruent to AC. It doesn't matter if the trapezoid is isosceles or not. But it needs to be the midpoint of one of the legs. So B is the midpoint of AC and E is the midpoint of FD. So the endpoints of the mid-segment are the middle, okay, the midpoints of the opposite sides. All right, and you can see that because it's marked congruent here and marked congruent there. But notice that not all four pieces are marked congruent because they don't have to necessarily be congruent. Okay, so two things that happen when you have the mid-segment of a trapezoid. One is that the mid-segment, EB in this case, is parallel to each base. So EB is parallel to FA, and EB is parallel to DC. That's the first thing. The second one's a little more complicated, and that is that it's half the sum of the lengths of the bases. It's like what? Half the sum of the lengths of the bases. Sum means add them together. What are you adding together? The lengths of the bases. So you're going to add FA and DC because those are the bases. You add those together, and half of that is the length of EB. So EB is half FA plus DC. So hope that makes sense because we're going to use that information to do example 3. It says in the figure, LH, which is the mid-segment of the trapezoid FGJK. What is the value of x? So here we have our x, okay? So what we know is that LH is the mid-segment. So 15 is equivalent to 1/2 the sum of the bases. So the bases are x and 18.2. So x and 18.2, all right? So now we have basically an algebraic expression and we just need to solve for x. But again, I want to reiterate that the mid-segment was LH and it's marked as 15, so the mid-segment should equal half the sum of the two bases, okay? So now, to get rid of the 1/2, we can just multiply both sides by 2, giving us 30 equals x, because they're going to cancel, x plus 18.2. We then subtract the 18.2 from both sides, and then we can determine that x equals 30 minus 18.2, which is 11.8. And that is how we solve for x. Alrighty, so now we're going to have you try this little guy. And basically we're looking for the x coordinate of point G. And the point, just remember that point G is supposed to be the midpoint of this side. So if you can use the midpoint formula to figure that out. And so we'll move on to kites. Kites, and we have our last example with our kites. Kites are basically quadrilaterals that have two pairs of consecutive congruent sides. So consecutive means that they're next to each other. Remember that? They're not opposite, parallelograms, the opposite sides are congruent. In this case, the opposite sides are not congruent, but the consecutive sides are congruent. All right, so our kites are basically where we have no congruent or parallel, opposite sides are not congruent, opposite sides are not parallel. So it's just totally like different type of quadrilateral altogether. However, we do have a couple of theorems for you. If you have a quadrilateral, if a quadrilateral is a kite, then its diagonals are always perpendicular. So we have a little 90-degree symbol there. So basically diagonal or AC and diagonal BD are 90 degrees perpendicular. Also, if a quadrilateral is a kite, then exactly one, okay, exactly one. That doesn't mean maybe one, sometimes two, no, exactly one. Only one pair of opposite angles is congruent, because again, in a parallelogram, both pairs of opposites angles are congruent, but not in the case of a kite. In the case of a kite, you only have one pair of opposite angles that is congruent. So like in this case, it would be angle J and angle L that are congruent. So angle K and angle M would not be congruent in this case. All right, so we're going to use that information to do example 4. And it says, dun dun dun, if FGHJ is a kite, find the measurement of angle GFJ. Where's GFJ? So they want me to find this angle right here. Okay, so I can use a couple of things. This was a while back. I think it was the first, second section of this chapter. We talked about the Polygon angle sum theorem. So the first thing I know is that this is a 4-sided figure. So 4 minus 2 times 180 is how many degrees are in this figure. So that basically means 2 times 180, which is 360. So I know that all of the angles in this triangle, or sorry, in this kite, have to add up to 360 degrees. And I already know 2 of the angles. So I have that, let's just go ahead and call this angle F that I don't know what it is. I'm going to go ahead and call it X. And the reason why I'm going to do that is because I can tell from the diagram that these 2 angles are not the same. This is 128 and this is 72. So that means that angle F and angle H are the pair of opposite angles that should be congruent. So if this is X, then this has to be X, because it has one pair of opposite angles congruent. So I'm going to put here that X plus 128 plus 72 equals 360. Because all of the angles in this quadrilateral should add up to 360 degrees. So now I'm going to get 2x plus 128 plus 72 is 200. And so then I'm going to subtract the 200 from both sides. So 2x is going to equal 160, and then we're going to divide that by 2. I'm running out of space here. And 160 divided by 2 is going to give you 80. So that means that the measurement of angle GFJ is equal to 80. Awesome. And then for part B, it says if, and this is a different figure now, if WXYZ is a kite, find ZY. Where is my ZY? Okay. I think okay, sorry here. My diagram is a little off. I put these letters in the wrong spot. Please don't shoot me. My children need me, so don't shoot me. We'll put the W over here and the Y over here, and I think everything's okay. Yes, all right. But that means that we're now looking for this longer segment here. Okay? It would have worked the other way as well, but we would have different answers from what the book had. So WXYZ is a kite, find ZY. So what we know is that in this case, the diagonals, XZ and WY, are perpendicular. And because they're perpendicular, what we have here is a right triangle, and we need to figure out what this distance here is, ZY. So we can use Pythagorean Theorem to figure that out. So we know that Pythagorean Theorem says legs squared, so our legs are marked 24 and 8, so 24 squared plus 8 squared should equal the hypotenuse squared, which is YZ or ZY. I hope that makes sense. So I'm looking at this right triangle right here, and here's one leg, 24, here's the short leg, 8, and the hypotenuse is what we're trying to find. So I'm using Pythagorean Theorem, leg squared plus leg squared equals hypotenuse squared. So we're going to solve this little equation now. 24 squared is 576. 8 squared is 64. And 576 plus 64 is 640. So now we square root both sides. And we're going to get that it's approximately 25.298. Alrighty, there's your zy. So in this case, we had to use a little bit of Pythagorean Theorem, and then we can find our missing measures. So now, I want you to try this little guy, do it yourself, number 4. And once you have completed this example, then you will have completed your notes for this lesson, and I will see you in class, and thank you for watching.